The box and whisker plot is also known as a box plot, and it is very important diagram, especially when it comes to understanding the distribution, the shape of a distribution of a certain data, which is quantitative, obviously. And uh, normally the box and whisker plot will have this kind of shape, something that looks a little bit like this. All right, let's suppose you've got something like that. So you would have two whiskers, and each of the box and whisker plot will lie on a certain scale. All right, your data x, your variable x, whatever it could be, which is quantitative, will lie on a certain scale, and these different values on the scale mean something. All right, these different values on the scale mean something. For example, here, this value here would mean the maximum in the data. This represents the minimum in the data. This one represents the lower quartile. This one represents the median. This one represents the upper quartile, right? So you will have a different information related to the box and whisker plot. Normally, when you look at a diagram like this, you will see that this distribution is positively skewed. Normally, you will know that the distribution that you have here is positively skewed by having a look at the third quartile and the second quartile, that is the upper quartile and the median, and having a look at the lower quartile and the median. If normally your third quartile, which is the upper quartile, minus the median is greater than the median minus the lower quartile, that is Q1, then you know that the distribution is positively skewed. That's one way of knowing it. The other way of, if you have a distribution that is like this, here, it's a little bit different. You will see that the third quartile minus the second quartile, in this particular case here, the third quartile minus the first quartile is less than the second quartile minus the first quartile. And when you have something like that, you know that this distribution is negatively skewed. And of course, we also have cases where the distribution is symmetrical. Symmetrical means the uh, difference, there is no difference between the upper quartile, they are equal on both sides, right? So the third quartile minus the second quartile is equal to the second quartile minus the first quartile. This kind of situation means that the distribution is symmetrical, all right, is symmetrical. So which also possibly indicates that your distribution might be normally distributed, which may indicate something like that as well. So that's a little bit about what a box plot is, what you want to do out of a box plot, you want to interpret it. But now you will note something, that as I said here, you have the maximum, you have the minimum here, all right? But you also have a revised box plot, which might look something like that, okay? You might have something that we call a revised box plot, where you can have such type of situation. Now you will see that, for example, here you will have box plot with these whiskers, but then you will have small uh, other values outside of these whiskers, right? You might have other values far from these whiskers as well, and these values they are labeled differently. You will see that they are separate from the end of a whisker here. They are separate. These are referred to as what we call outliers in the data. They are also referred to as what we call outliers in the data. And what are outliers? Outliers are values that are uncommon in the data, and you can identify it from a box plot as well. And To identify an outlier from a box plot, you will need the concept of what we call the lower fence and a concept that we call the upper fence. Through these two, you will be able to determine if there are outliers in your data. Then, if this is the case, you need to understand that this value does not represent the maximum anymore, and this value does not represent the minimum anymore. Okay, what do they represent? I will just get back to that in a moment, but first of all, I need to explain to you what the lower fence and the upper fence mean. The lower fence normally determines a sort of boundary which, if any value goes beyond this boundary, it will be considered as an outlier. So it's like determining a sort of boundary which determines whether there is an outlier or not. For example, when we refer to the lower fence basically means that you need to take the lower quartile in your data, you subtract 1.5 times the upper quartile minus the lower quartile. This is what the lower fence is about. The other way of seeing it is that it is the lower quartile minus 1.5 times the interquartile range. So you look at the distance between the upper quartile and the lower quartile, you multiply by 1.5, and then you will take the lower quartile here, you subtract 1.5 times that distance. And when you subtract 1.5 times the distance, let's suppose you get the lower fence is somewhere here. It's a value that you get here. Any value that will go below that lower fence will be considered an outlier. And the next value will be considered as the minimum in the data here, but it's not really the minimum. Okay, it's the minimum after the lower fence. And then for the case of upper quartile, if you have noted what I've done, the upper quartile will be basically the upper fence, excuse me, would be equal to the upper quartile plus 1.5 times the interquartile range. So it is going to be the upper quartile, which is here, plus 1.5 times the interquartile range, and then this gives you a boundary, and any value that goes above this boundary, like let's suppose here, becomes what we call an outlier. So that's a little bit what the revised box plot looks like, where you can get an idea of the outliers that exist in the data as well. From the traditional one, you may not find the outliers because the minimum may be an outlier, but you won't know it. But from this kind of revised box plot, you will get an idea of your outliers that exist in the data. So we are going to do something. We are going to do an activity where we are going to check to apply a box and whisker plot and see what we get. Okay, so this is the data that we are going to work out. uh, just for your information, this is what we said. We are going to draw a box plot for the data from the previous slide. In fact, I repeated this here, but you will have to draw a box plot here. Okay, and in addition of drawing the box plot, I will also represent the lower fence. I will also show you where the upper fence is as well in R. We're going to do all this in R. So this data represent the monthly income of CEOs, for example, of software companies for a certain year in rupees. All right. So we're going to work this out and see what we get in R. That is, we're going to do a box plot for that. So first of all, we'll need to write down all our data. As you've seen, you need to get your data prepared. So we have all the data that was on in R. All right, we got all the data that was in R. Here we go. I've rewritten them here, and then I'm going to apply the box plot now. In fact, if you want to do a box plot in R, it's very simple. You just need to use the function box plot, and then you will use the data that you have called X and then you can just do enter and you will see what kind of box plot you get something like this. All right, but of course, generally you work with a box plot which is horizontal. That's the first thing, and the other thing is that these axes should be on the horizontal as well. We need to get this axis on the horizontal axis, and you will see that there is an outlier as well here that appears. Okay, so let's have a look at the data from the horizontal perspective. If you want to draw the data from an horizontal perspective, you need to add an argument to the function that we call horizontal, and you will say that it is equal to true. By doing so, you get your uh, box plot on the from an horizontal perspective, where you will see that there is an outlier on the right. But if you want to see the outlier more clearly, you can just change the point character, which is a default here, circle. Then you can put it as a dot, which is a full circle, like this. All right, it will be more clear that there is an outlier going on the data. The other thing that I might want to do if you want to improve this box plot is to remove that old box around this old frame rather around the box plot. You can do that on this data, and if you want to do remove this frame, you'd say remove frame by using the argument frame.plot equal to f, and then you will see that the box plot disappeared. All right, the other thing that you will see is that it starts from 50 to 300, but there is a kind of information that is kind of missing here. You see, you don't have a you don't have a zero value, for example. It starts from 50 here, but what about this minimum here? So maybe the best thing to do is to start the axis. Now start the axis here from 0 to 300 instead of 50 to 300. But note something, you will have to be careful. You can't put x lim. Don't think that this is the x-axis. This is still the y-axis, but it has been transposed because we said we want to work with horizontal to true. We said that we want to represent it horizontally, but still this is originally not the vertical axis. Originally this is the vertical axis. It is not the horizontal axis. So this is why if you want to change the x-axis, not the x-axis, the horizontal axis, don't put x lim, but put y lim equal to c0 to 300. Don't put xlim as I said to you because originally R does not recognize this as a horizontal axis. It recognizes it as a vertical axis. It's just that you have transposed it by using this function. So this is why I don't put xlim, but I put ylim 0 to 300. Here we go. We get our box plot, which is a little bit more clear and more neat. That's a little bit what we get. Now, you have seen that the box plot has highlighted an outlier here. Now, why did it highlight an outlier? It means that there has been a certain value that has gone above the upper fence here that I just explained earlier. So what do we need to do? We might want to know what is the upper fence. Normally, it's not necessary. You can just ask how to do this as it is here and you are done. But let me just explain to you the concept of upper fence and lower fence again. To be able to understand the concept of upper fence or lower fence, maybe the first thing that I want to do is to summarize the data to find the lower quartile, the upper quartile, and the different quartiles. All right, because I will be able to calculate the lower fence, I will be able to calculate the upper fence from these different information, the median, the lower quartile, and so on. And when I've got these different information available, then I can compute the lower fence and the upper fence and draw it on the a diagram here. I repeat, this is not necessary. I'm just showing it to you so that you understand why this has been classified as an outlier. Because you would like to know whether there is a kind of a percent somewhere here, which means that this is not the maximum in the data. This is not the maximum. This is the maximum, but this is an outlier. Let's find this. One of the things that you can do is to do a summary of your data. X by doing a summary of your data X, you get the different quartiles in your data. If you type S, you will see that you get the different quartiles starting by the minimum, the first quartile, the median, and so on. Okay, so what we want to do here is we want to find the lower fence. What is the lower fence? Is the lower fence 0, 10? Is the lower fence whatever value? Is the upper fence 200? What is it? We want to find these different things. So let's find the lower fence first. The lower fence, as I said to you, is the lower quartile minus 1.5 times the interquartile range. So what is the lower quartile here? The lower quartile is the second value from the object S. So if it is the second value from the object S, you can just say S2, you will get the second value only, which is the first quartile, 46. If you say S, for example, 5, you will get the third quartile, right? 1, 2, 3, 4, and 5. In the array here, the fifth position represents the third quartile. So in the array of S, the fifth position represents the third quartile. So what we want to do, we want to find the lower fence. Let me call it LF. And this is equal to the lower quartile, which is S2, minus 1.5 times the interquartile range. And what is the interquartile range? Interquartile range is S5 minus S2. S5 minus S2, as you see here, right? S5 means the third quartile minus the lower quartile here. So lower fence is negative 1.25, so it's some value that is going below 0. And in this particular context, you won't have anything that goes below negative 1. So this is why you don't have any outlier that goes there, because obviously you are talking about salary, so there is no negative value. So this lower fence doesn't mean much, but still I'm going to plot it for you in a moment. And then you do the same thing for the upper fence, where the upper fence is the upper quartile side plus 1.5 times the interquartile range that we just did here. 1.5 times the interquartile range. Let's have a look at the upper fence. You see that it is 124 plus 75. So the upper fence, do not worry about this, please. But the upper fence is 124 plus 0.75. Any value that goes above 124.75 becomes your outliers. Right. So what do we want to do next? We want to plot these lines. So if you want to plot these lines, the first thing is that you need to have a plot ready, which is already there. And then you will plot these lines here by using the function abline. All right. Abline is a function that you can use to plot lines using a certain information. Like, for example, here you want to plot a vertical line. A vertical line at what axis? At what point on the axis? At one point at negative 1.25 and also at 124.75. So we'll start by negative 1.25, the lower fence. So then what do you do if you want to plot a vertical line here? What you do is you say v equal to, and then you decide where it should plot that line, and it vertical line. It should plot it at negative 1.25, which means that at the lower fence. So you say v equal to LF. And if you just do that, you will get a full line, but you might wish to have a broken line as well. And if you want a broken line, to make it a little bit more neat on the diagram rather than having a full line here, you might want a broken line like this instead of a kind of line like this. So then if you want a broken line, there is a type of line that you can use which is equal to 2. I am used to these different arguments, but you may wish to go online and try to see what are the different line types that you have in R. So you can type LTY in R on Google and you will see what are the different types of line you got. So if we do LT2, you will see that the broken line is here, which means that the lower fence is here. And then we can do the same thing now for the upper fence. Here we go. And you will see that the upper fence is here. So any value that is beyond this boundary here, the upper fence, will be considered as an outlier. So if any value was above 124.75, it will be considered as an outlier. If we look at our data set, you will see that there is only one value that goes above 124.75. It is 300, and this is why it has been tagged as an outlier. Otherwise, the rest stays within the boundary, so there is no outlier tagged. So that's a little bit about the box plot, and you will see in this particular context, you clearly see that the um, upper quartile minus the median is bigger than the median minus the lower quartile, which means that this distribution is positively skewed. So the distribution of salary is positively skewed with an outlier in the data. That's what the interpretation is about for this box plot. So that's all for the box and whisker plot.